All right, welcome everybody this morning. Our speaker today almost needs no introduction. Mark Horowitz received his BS and MS degrees from Massachusetts Institute of Technology and PhD from Stanford University, where he is now a faculty in the electrical engineering department. He's had many academic accomplishments. His career really started off, I believe, in more of the digital world, doing looking at digital systems and CPU architecture back in the early 80s. And it's really evolved into some of the topics he looks at now are very broad in both digital, analog, and mixed signal systems. A lot of them are integrated systems. He was the department chair of the EE department for a few years recently. He has many awards, many accomplishments, and I'm not going to go through all of them. But a few notable things, he was elected to the National Academy of Engineering, which is very prestigious. And also, I thought something that was interesting, he's in the, recently it looks like he got into the American Arts and Science Academy, which is pretty interesting for an engineer, I think. As many faculty at Stanford, Mark also is very much an entrepreneur. And in that regard, most notably, he started a little company called Rambus, which has grown into a larger company. Really, it focuses on high-speed access to memory. So many of the PCs that you have and the laptops are based on some of the architectures that really have been developed by Rambus. So with that, I will let Professor Horowitz take it away.
Thank you very much. Thank you very much, Chris. Today, I'm going to be talking about some of my research effort on what I call digital analog design. And as Chris said, and I'll talk a little bit in the talk, my background really was a digital designer. And then I got involved through my work at Rambus in building relatively sophisticated mixed signal systems. And through that, I came to the conclusion that we really need to change a little bit the way we think about analog design. So why is that? I think that we all will agree that chip design is basically growing up. Now, none of you are probably old enough to know this, but when I was a kid, back in the ancient times, AKA in the 70s, integrated circuits were a relatively new invention. And they came in these little packages called DIP packages, and they had a couple logic gates on them. And we've transitioned over the past 30 to 40 years into something that had a few logic gates on it into a modern SoC design, which has billions of transistors and integrates both analog and digital systems. As a result of this evolution and basically growing complexity of chips, basically the requirements on the analog systems are growing much more severe. While before people were happy with maybe 8-bit DACs or ADCs that ran at megahertz, now people want bazillion-bit DACs, I don't know, 16, 18, whatever, at lower frequencies. And at high frequencies, people are talking about converters that run at many gigahertz. Okay? Now, while we have many more transistors, anybody who's involved in mixed signal design knows that as you scale MOS transistors, they don't necessarily get better. They're FTs, their speed improves, but the matching is worse, the voltage ranges are worse, and so you have a lot of additional complexity you need to work on. But probably the biggest thing is that if you look at a modern, this is a modern analog chip over here, what you find out is that, yes, there are some analog circuits, but typically it's covered with a lot more transistors that are digital, because the analog circuits are a component in a bigger digital system. So how do we deal with that? Well, we deal with these growing complexity by taking advantage of the fact that we have a lot of digital logic around us, and that digital logic has scaled in performance and in energy so that it doesn't cost very much to use it. We've gotten to the point where I tell my students it is impossible to build a circuit that meets the specs that you need to build. Okay? So what instead we should do is build a circuit that is adjustable or tunable and build measurement circuits so we can tune the circuit into the range of performance it needs. Okay? This is generally called digital assisted analog, and there are many people in the country who have really pushed this design forward. one of the foremost is my colleague at Stanford, Boris Merman, who has shown how you can correct not only for offsets and various other things like that, which were conventionally done, but also for nonlinearities in the systems by doing more sophisticated digital correction. This has led to a rethinking of what you need to do in an analog circuit rather than building an ADD converter that is extremely precise or extremely accurate. We can then do something that has the resolution we need, even though it may have some nonlinearities, and use system properties to basically back correct that converter to get the data that we need. This is called digitally assisted analog or system-directed analog. Okay, and is basically almost any analog system you see today, that's what they do. So the question is, are we done? Is that basically the best we can do from a CAD perspective for analog design? Okay, and that depends on how much analog circuits you really need to do in these digitally assisted, system-optimized analog. Now the problem is that these systems are still going to have some analog, and they're going to have lots of digital circuits around it as well. Okay, so the question is it easy to build these combination digital and analog circuits? And are there tools that we could build in this new environment that would make these designs easier? And that's basically what the talk's going to be about. To motivate this, I'm going to humor myself, and I hope you, by a brief trip through memory lane for me, because I'm actually getting to be an old fuddy-duddy. My first design, which was in the mid-'70s, was a digital design, because I started off as a digital designer. It used those integrated circuits that had a few gates in it. My design tools were one of those plastic templates and a piece of paper and a pencil. And I drew schematics that looked like this. It's actually a copy of a schematic I drew, right? And then I was actually too poor to even do wire wrapping, which was the right way of putting together things at the time. And there was this cheap alternative called a wiring pencil, which had that spool. This thing over here is a spool of extremely fine wire. It had insulation on it that melted at solder temperatures. So you basically wrapped it around the pins of sockets. And then you soldered it, and the wires connected where you soldered it, and you could wire things up. So that's the way I wired things up. And when I graduated from that, in 1978, I moved to Silicon Valley, and I got involved in integrated circuits. Okay, design tools were not much better than I had used previously. I again drew schematics on pieces of paper with pencil, right? We did have computer circuit simulation. Okay, the layout person drew a stick diagram of what the elements were going to be, hand drew it on pieces of Mylar, which were then digitized. Okay? Now, if I think about the design style that we use for digital design, and I compare it to how we do digital design today, we have really changed everything. Almost nobody draws things on Mylar anymore. We basically write programs called Verilog or System Verilog or a C derivative. We do some floor planning at the top level, and we basically generate the chip. And if you think about that process from the early 80s, late 70s to today, we moved through many phases. We started with SPICE and custom layout. We did the logic and standard cells. Then we did synthesis and automatic placement routing. And then we went to SoC design and used macro blocks to increase the complexity of the design so that we could deal with. Okay. Yet, when you look at analog mixed signal design, the transition over that 30 to 40-year period has been much less dramatic. Okay, it is true we do not draw schematics on pieces of paper anymore. We draw them on a computer. And we do not draw layouts on pieces of paper. We draw them on a computer. But we are still drawing the schematics and layouts, and the process is still very manual. When I looked up layout designer on the web a couple years ago, this picture of this guy came up. He was a layout designer for Micron. Was designing, he was designing some DRAM circuitry. So the point is that if you think about analog design, it's still incredibly manual the way we handle it today. Okay? And this causes a huge problem in today's chips, because even for an analog chip, right? So this is an analog chip. It was in 2009. It's basically a multi-band receiver. But if you look in that multi-band receiver, which is an analog portion of the chip, there's a huge portion of digital logic in there. And that digital logic is doing all the correction and adjustments that make the analog circuits really work. And therefore, to test out this analog system, we need to actually run it with the digital logic. Does that make sense? OK, the fact that we have to run these together brings up what I call the modeling problem, which is the key problem in validating mixed signal circuits. So if you ask an analog designer, what matters? Does the implementation, the transistors, represent the circuit, or does the model represent the circuit? Any analog designer will look at you like you have two heads and say, you idiot. We build the implementation. That is what matters, right? The model that's just the model. It's to help us think about it. But it's not the truth. The truth is the implementation. When you ask a digital designer about a model, they believe the model, because what they write is the model of the circuit. The implementation is done automatically through synthesis or the people who implemented those SoC blocks. So they think if the model and the implementation don't match, you basically fix the implementation. It's a bug in the tool. But for analog designers, they think the model's model. No one would be so stupid to believe the model. Okay? But the digital guys run system validation, and so they basically build models for the analog circuits. And as a result, this leads to a whole bunch of bugs in mixed signal chips. Okay? I have been involved in a number of companies that have done mixed signal designs, and I have lots of friends who design mixed signal chips. The most embarrassing thing is to design a chip where the whole chip comes back, and the analog works perfectly, and the analog designers are really happy that this complicated Wi-Fi system works. But the system doesn't work because there's some inverter gates someplace screwed up, or there's a polarity inversion in the overall system, so the digital can't actually control the analog like it was supposed to, right? And those problems arise because the model didn't correspond to the actual implementation that was used for the top-level validation. Or even worse, the top-level validation wasn't done. So to solve both of these problems, to try to address this really critical problem in mixed signal validation, and to try to move analog design tools forward, my group has been thinking about how to do improved analog design methodology. And we've come up with this notion of digital analog design. Okay? And I know that sounds like an oxymoron, because how could you have digital analog design? Analog is one, digital is the other. But the idea is to not try to improve analog design by just using more digital gates. Make analog design more like a digital design process with a lot of the tools and checks that digital designs have that allow them to basically work at a higher level. So the goal is to really make analog design more like digital design. And what I mean by that is to better encapsulate the functions of the analog design so we could deal with abstractions at higher levels, to create methods of validation for analog designs that are similar to validations for digital designs. Now, I am not saying digital designers don't make mistakes. They make mistakes all the time. There are these really subtle logic bugs. But I am telling you that digital designers never make the same mistake twice. And the reason they don't make the same mistake twice is when you make a mistake in a digital design, there's a whole team that gets put in place to figure out how that mistake could have possibly happened. And they write some tools to make sure that you never make that mistake again, and nor does anybody else. So when you tape out a digital chip, there is this whole long list of tape out checks that you have to run through, and you ask, why do I have to do this check? And it's basically because somebody didn't do that once and something didn't work. So how do we basically sort of allow ourselves in analog design to prevent us from making the same mistake twice? And that is going to require automatic electrical rule checking, which is something that digital systems do. And ultimately, we want to basically enable us to do better reuse of components. Does it make sense? OK, so to summarize, what we need to do if we're going to make analog design more like digital design, we're going to have to be able to create effectively analog standard cells. But what is an analog standard cell? Because no two analog cells are ever do the same function exactly. It's not like I have an AND gate. I always need the same AND gate. So what is an analog standard cell? What's a reasonable abstraction? If I'm going to try to not work at the transistor level, what level do I work at? How do I build functional models that actually can correspond to these things so I don't get stupid logic errors? And that's going to require me to do equivalence checking between these models and the actual implementation to make sure that they actually correspond. And finally, how do I do statistical analysis? In digital circuits, you basically build the logic. You approximate it by a logic function. And the logic function always works if in these range of parameters. But analog circuits have numbers. The numbers are never the same. So how do I basically make sure that with process variation and whatever else, the system's going to work? OK? Does that make sense? And I claim if I can do all these things, I can really elevate analog design. And so the rest of the talk, I'm going to go through and sort of try to deal with each of those issues. So let me start with standard cells. So I want to make an analog standard cell. But the problem with an analog standard cell is unlike a digital standard cell, where I have a relatively limited set of functions, and I need them in a couple different sizes. Analogs, you have analog parameters that you want to tune. So if I give you an implementation for an analog cell, even if it was a really good implementation, you might want a slightly different power level. You might want different bandwidth. You might want different parameters. How am I going to give you those parameters? So my claim is that even if someone gave you the exact right thing, would you trust it? And the answer, if you ask any experienced analog designer, is no. OK? And the question is, well, why not? Because digital guys trust the digital standard cells. And the difference is that in digital cells, you have a set of electrical rule checks that you run. And if your circuit obeys those electrical rules, then they guarantee that the function that the person said it has is really all you need to know. In analog cells, analog design, there's no standard cells. There's no electrical rule checks that you can do to make sure the spec that they give you or what they said about the thing actually is true. So in thinking about this and thinking about the fact that basically you want to change a lot of parameters, the most valuable thing about an analog standard cell is actually not the implementation. What experienced designers do better than inexperienced designers is how they test the cells, right? Because you can look up in a book a whole bunch of different topologies. But what rookie people do is they build things that have sensitivities that they just didn't check. So I claim that if you really want to build an analog standard cell, what you need to do is not only provide the schematic, but you need to provide a list of checks that you did to validate why you think that thing's good. Because then I can look at your list of checks, and I could say, well, is there something that he didn't check that I think you should check? In which case, I can add it to this list, this growing list of things. And if not, then I'll trust your design, because I'm not trusting your design. I'm trusting your checks you did. Okay? And the two kinds of checks you need to do is the ones you typically think about. These are the test benches that you need to extract the parameters for the data sheet. But the other kinds of tests that you need are assertions. Because what's an assertion? Assertion is the assumptions you made when you ran the first kind of tests. Because when I measure the gain of an amplifier, I'm measuring it for a certain common mode input range or a certain output range or something. So I need to know what those are because, or a certain power supply, because if I use that cell in a different environment, those checks might no longer be valid. Okay? And those assertions then must be used in the Verilog or in the model to make sure that in every instance that you use the cell, you're not basically screwing up its environment. So I claim to reuse analog cells, we need to record and archive the test benches and the assertions as well as the schematic. And I think the schematic is the lesser important of those things. Okay? Now, these will be specific to classes of cells. So there's not an electrical rule checker in general for every analog cell, because when you build an RF system, that might be very different than an amplifier, might be very different from other things. But within a class, there's probably going to be checks that will be shared. So all amplifiers, you're probably going to measure a couple things. So we're starting to build an archive for these checks, which we call circuit book. And it's hierarchically organized in terms of classes of circuits. So the goal would be, if you're trying to build a new phase lock loop or some timing circuit, you can look at the timing circuits that have already been built and leverage those checks that are generic to that class, as well as adding additional checks that you need. Okay, so the whole point here is to try to reuse checks so that when someone comes up with a new circuit, you don't have a new designer making an old mistake. Okay. Because the checks that were done to catch that old mistake are still present in the check file, even if you do a new schematic. Does that make sense? So I think if we do that, we will get effectively analog cell reuse or design reuse, which is really what standard cells are about. Okay. But if all we do that, we're still manually creating the cells, and we're manually putting together. So we need to do something else. So the next thing we need is an abstraction. Digital tools use abstraction really effectively. Basically, we think about not the voltages and not even the delay in general. We think about voltages and synchronous systems. Some changes occur. On the next cycle, we do something else. That allows us to work at a much higher level, allows us to work at kind of Verilog. And we have tools that do the timing and the detailed electrical checks. Which means that a digital designer is never complaining that they want a faster SPICE simulator. Analog tools have no abstraction, so they basically use simulation at the transistor level. And when you ask an analog designer what design tool they really want, they often say they want a faster SPICE simulator. The problem is that we will never have a fast enough SPICE simulator to do everything that you want. We're going to have to do some sort of abstraction. So what abstraction should we use? I think the way to answer this question is to think about what makes an analog circuit analog. Why is an analog circuit analog and not digital? Or why is a circuit digital, not analog? What's the difference? What's fundamentally has to be true about every analog circuit? Excuse me?
Quantization.
I just...
Lack of quantization.
Yeah, that's...
Lack of quantization.
Or discrete versus continuous.
Right. So the thing is, digital results are not smooth. That is, an incremental change in an input can make an enormous change in output. That's what makes it digital. What makes it analog?
Continuous.
Right. The output surface is continuous. An incremental change in input causes an incremental change in output. Okay. What that says is all analog circuits have smooth output surfaces. Okay? That's fundamentally what makes a system analog. So we should be able to leverage that in the way we think about analog circuits. Okay? So, I have a joke that if you look at something that looks like this, is that analog or digital? Well, it depends. If your inputs go from here to here, it's digital. And if you're looking in this region, it's analog, right? Because everything in the world is continuous. There aren't really any digital gates. It's just the region that you operate them in. OK, so how can we use this fact that the analog result surface is smooth to our advantage? Well, look, in a digital system, the biggest problem you have in a digital system is exploring the result surface. Because just because you know the answer in one point doesn't mean you know anything about the adjacent point. It's discontinuous, right? So you have to explore the whole space to figure out what function it is. What's true about smooth surfaces? actually a low density sampling of the result space will give you a very good prediction of what that surface is, because it's smooth. So the problem in analog circuits is not sampling the output. It's not exploring the space. It's characterizing what the space is. Make sense? OK, so if we want to make a model, we want the model to exploit the fundamental feature of the system. So in digital, what we say is we forget about the fact that there is transition regions. We say the fundamental point about a digital system is that it is discrete. So we model as completely discrete. So the fundamental thing about an analog surface is that it's smooth. So we're going to think about modeling that smooth surface as a piecewise linear system, because any smooth surface can be modeled by piecewise linear. Okay? Now, I will say that the reason I believe that this is a good idea is if you think back to any of your analog design courses, how do they teach you to analyze analog circuits? Small signal analysis, right? So how do they give you specs of analog circuits? They're all small signal specs. They're all doing the piecewise linear thing. And they also give you distortion. Sometimes you have to worry about deviations from the linear behavior. Okay, but that's the way every analog designer I know talks about an analog circuit. So we are already intrinsically doing that. We're just not, we're timid about it, I guess. Now, look, I know real circuits are not linear, and I'm not saying you're not going to run SPICE simulations on your individual circuits to make sure they work. But what I am saying is digital circuits are not Boolean either. And the whole point of creating a model is to validate the designer's intent. We want to ensure that what we're building or what we built match the specs. If the specs are linear over some range, remember we have constraints. Piecewise linear, we can have multiple slopes. We can specify the function to the fidelity that we need to validate the overall system operation. Okay, subtle analog issues are going to still be done by simulation at the small block level. And I will say that there are analog circuits that appear strongly nonlinear, but we're going to linearize them using what I call domain translation, or by modeling them as coupled linear systems. So I'll give you two examples of systems that appear highly nonlinear that are actually easy to handle. So the first one that looks highly nonlinear is a standard clock PLL. So for those who don't know, a PLL is just an analog system that takes an input clock and creates an output clock that is some frequency multiple of that or is in some phase relation to the input clock. And its input is basically a square wave, and its output is basically a square wave, and there's no frickin' way that's a linear system. So if you look at just the phase lock loop, that's completely nonlinear. And if you try to model that system, it's going to be very hard if you think about it from a voltage in to voltage out perspective. But if you've designed phase lock loops, you realize that the specs for phase lock loops are generally in terms of what the phase transfer functions are. So you look at the phase of the input waveform and the phase of the output waveform. And if you look at from phase in to phase out, that is, in fact, a linear system or can be easily modeled by a linear system. Okay, so we can write the system model for that as a linear system in phase space. And then in the simulator, we still have square waves in and square waves out, but it's linear in phase, not in voltage. So that handles a whole class of nonlinear systems. A duty cycle corrector, this is just takes a square wave in and a square wave out and changes the duty cycle of the square wave. If you look, it's highly nonlinear, but if you plot duty cycle versus control voltage, you get a very smooth plane. So it easily works in that space. Okay, so the other place that people complain that things are really nonlinear is something like this. Okay, remember I'm building controllable systems because I can't build anything accurate enough or precise enough. So I have a gain of an amplifier, but the gain is a function of the bias current, and I put the bias current in, and therefore the output voltage is going to be the input voltage times some function of the bias that is clearly not linear. right? Linear is plus, no multiplies. So anybody who has built a system with an automatic gain circuit in it, how do you analyze it? What do you do? Okay, now I'm sure there are some people out here who are really brilliant and can solve nonlinear equations in their head. Okay, but I'm not. And so what I always do is you make the control loop and the signal bandwidth discrete. And you think about what happens when the signal basically goes through as kind of, it's going through in a quasi-static sense. And then you look at what the control loop does. And that's how you basically design the system. So you break it into two quasi-linear systems. And that's the way you think about it. So what we do for a coupled nonlinear system is we basically assume the tune parameters are static or slowly time varying. And we break it, again, into two quasi-linear systems. And we validate the two quasi-linear systems agree between the model and the implementation. Okay. Now, if the control varies rapidly, it will adjust the output rapidly. We don't validate the time interactions between that. Okay, so that's the thing that we don't validate precisely. And if that was critical, we probably could think about that. But in no systems that I know of so far is that a critical design parameter. OK, so I hope I've convinced you. I don't think I've probably convinced you that this piecewise linear model is sufficient. I hope I've caused you to think that it might be possible. Because I believe it is possible. I've been giving a talk on this topic for a number of years, always challenging the audience to find an example where this couldn't be done. I'm happy to say that only one example has come up so far that I think is really interesting to work on that I haven't quite resolved. And that's doing distortion correction in high-performance amplifiers, where you have to pre-distort the input to get a linear output out. I think it probably could be done, but that one, I'll grant you that maybe the nonlinearity in some time-nomadic fashion is important. But for everything else I've seen, it seems like it's pretty easy to fit this framework. So what we've done is we've said, OK, if we have this kind of approximation or abstraction, how could we leverage it to make analog design easier? So if I have an abstraction, then I know what a functional model needs to model, because it needs to model the piecewise linear behavior of the underlying circuits. And so the next task that my students worked on was how do we build piecewise linear models for analog circuits that will work in a digital validation framework so that we can do the whole system simulation fast enough to validate the system. OK, so let's look at functional modeling. OK, the goal for analog functional models has to be pin accurate, right? Because we're going to need to basically take the implementation of the circuit and the functional model and do a comparison. Because if I can't compare those two things automatically, there's no guarantees that the whole system simulation makes any difference, right? All the digital cells are validated against their functional models. So we need to do that for the analog. So it means it has to be pin accurate. It has to be low complexity, because if it slows down the digital simulator, who, those guys have to simulate billions of vectors or whatever, they'll not use it. So it has to be fast. And it has to, therefore, be compatible with the event-driven simulation that the digital guys do, because they're the people who are basically running the whole system. Now, it's also true when you have this analog correction loops. The problem is it can take thousands or tens of thousands of cycles for the correction loop to actually lock. And so you need to run long times to make sure that your correction loops don't have weird interactions. Even though your system is working at a gigahertz, you may have to simulate very long periods of time to make sure the analog corrections work. OK, so you need fast. OK, so our problems are the functional models must be event-driven and unidirectional. And we have to represent, in this event-driven framework, signals that are continuous. So how do we do that? OK, so the way we chose to solve this problem is to basically break it into a couple small problems. The first thing we did is we have to deal with the fact that simulators are unidirectional. So if you think of an event-driven simulator, something happens to the input of a gate, and that causes an output to happen. There's none of this communication, let's figure out what's going on. The models are all unidirectional. So if I have an analog system, I have to break the analog system into unidirectional blocks where any feedback has to be slow compared to the simulation time, or the time step of the event-driven simulator, which could be pretty long. So what we do is we tear the analog circuits into blocks that are mostly unidirectional, which means that we break all tightly coupled feedback has to be incorporated within a model. Now, with an op-amp and feedback across the op-amp, that feedback is slow enough in general that you don't have to put that within the model. You can have a model of the op-amp and put feedback around it. But for tight coupled, for high frequency feedback, it has to be incorporated within a model. So if you have a circuit that looks like this, where you have a sampler, so this was an ADC converter where we sampled a voltage on a capacitor, and then we ramped the voltage on the capacitor to measure how long this was a voltage to time converter. Right? So we create a time delay which is proportional to the voltage. This whole circuit has to be in one analog model because I have to have all that coupling in my model. I can't break the current outside. Okay. So the first thing you do is you run through and you basically tear apart the design in terms of things that are source-drain connected components, which is similar to the way you tear digital systems. And that will yield modules that are unidirectional that we can then think about writing a model for. But once we do that, how do we represent the analog waveforms? So we're going to use a piecewise linear approximation because that's easy to do. So at every event, I just don't tell you what the voltage is. I tell you the slope at that point. And as long as the slope is relatively constant to that thing, I don't have to put another event. When the slope changes, then I have to put another event. And so my models have to take piecewise linear inputs and generate piecewise linear outputs. Okay? And the events that I pass around in System Verilog are just things that are basically have a voltage and a slope. And System Verilog allows you to pass structures, so this is not a problem. It easily passes along a wire. So we want to be able to compute the outputs relatively quickly. So we leverage the smoothness of the analog output surface and the fact that it's linear, and we create a linear model of that, which means that the output response will be a sum of exponentials. And we basically compute for a piecewise linear input what the piecewise linear output will be for that, or what the exponential output will be. And then we schedule the longest time that we can that's within an error bound, and we basically schedule that output. OK, so we have fully Verilog models that run that have good fidelity to the analog underlying circuits. This is just some of the math that we do. And so because the inputs generally cause exponentials, we cause different segments, and we basically use error tolerances to allow the sampling at the end to be less dense. And we can effectively and with relatively high, with good precision and small delay, calculate the response of a bunch of analog systems. And if you're interested, there was a paper written by my student on this, and we've improved it. So in summary, we've created a functional modeling environment that can run in a digital validations thing, and we can create fast event-driven functional models. Okay.
What is it you're really buying at the end of the day? I mean, if you store the voltage and the slope at each time step, if I understand, the precision that you're going to need, the accuracy in the slope and the value of the voltage at that time step is going to need to be very high, just as high as whatever. Yeah, let's say we take a PLL. We're trying to model something in phase noise.
Yeah, so let's take a phase-like loop because it's actually a very good example. So the question is, look, if you're modeling everything in voltage and everything else, you're going to need very high precision. Given that high precision, how could this ever be faster?
Yeah, that's the question.
Right. So the answer is we don't do that. So when we model a phase-lock loop, what we do is we basically model the signals come in, they're digital signals because they're clocks. we go to basically a phase detector, which could be modeled in a digital way. We just put precise delays within the phase thing. So that's all digital simulation. Okay, from that, we get basically 2 timing points. So the charge pump capacitor is something that we model, and we model basically charge injection from the switching things, but these are not circuit simulation. These are, you get this much charge injection when these guys switch, right? Because they're stereotypic waveforms at that point. So you add, for every event, you add a delta on that capacitor voltage, okay? But the most important thing is that from that voltage, we just integrate that voltage in terms of phase directly, and that's what generates the output waveform. And when the integration of phase crosses 180 degrees, we generate the output. So the whole VCO circuit is basically approximated by a transfer function from voltage to phase. And so that simulation runs incredibly fast, and you can run full lockups of your loop. And it basically, if you put noise in the system, where you add random noise for the various things, you will get it. You will get the subharmonic spikes that you get because of the injection from the switches. So, because if you're doing a multiplying phase-like loop, you get all that stuff because you get this delta every time the switch occurs. So all the big artifacts that you worry about happen in a simulation that is incredibly simple to do. So the difference is that when I model an amplifier, I'm not modeling all the stages of the amplifier necessarily. I'm modeling the amplifier and building a linear model of that, which maybe has some distortion in it. And so I'm doing this block modeling, and my time steps are not the time steps that you're thinking about in a SPICE-like simulator. My time steps are just what is the time step I need so my output waveform, right, has some error. So we can show you examples. For RF circuits, the most important thing is you don't model the carrier. Well, the carrier is the carrier, but you don't have events to generate the carrier waveform. Does this make sense? Because that's...
I would argue in RF systems, I agree with you. I'm not sure about your last statement, what that exactly meant. I agree with you. The carrier is probably something we're least interested in.
Right.
It's the other things that are out there that kill you, right? And the level of precision that you need to...
Well,
I mean, one part in billions, right? Some charge injection at some node that, I guess your model would have to incorporate all that, right?
Well, so here, remember my basic assumption. I am not trying to build a simulation environment that will prevent you from making a mistake you've never seen before. Because I believe nothing will do that. SPICE won't even do that because you're not looking for it, you won't find it. What I am trying to do is for everything that you've seen before, I want to make sure you don't make that mistake again. If there's an extremely sensitive node someplace that one part in a billion is going to screw you, I think you're screwed anyhow, because I don't think that circuit's ever going to work, but we can talk about that. But if you knew about it, then we could do that. Once you know about substrate coupling, we can model the substrate coupling path. We don't have to put the entire substrate model in, because somebody does that, and we extract a model from that that just has a transfer function through it.
So are there 2 phases in this design? Would you, if we were starting from scratch, let's say we're using your tool, and we're starting from scratch in a given technology, would I then create these abstract models for, say, a new technology and a new design, and I get these abstract models, and then I run with those for the design, the remainder?
So the question is, how do we really use this methodology for real? I mean, come on. Okay, so the answer is, what you would do is, if you were the first person to ever use this methodology, you have a lot of issues because you have to construct everything from scratch. Hopefully some of the testing. Okay, so what we do is we basically take this, we have an expert, so the expert says, look, these are the things you really need to model because these are the things that screwed up before. So you write functional models that have, this is the way analog designers work. You write functional models at the higher level that basically model the things that you think you're worried about. You tweak around that at the higher level until you get a system that you think should work. Okay, the difference is that in modern analog design, once you do that, that gets thrown away, and you start working on the real stuff, which is the circuit, and that's what ends up being maintained. The other thing gets obsolete. What I'm saying is you work now on the circuits, and now what I'm going to talk about next is how do you basically validate and update this model so it constantly tracks the circuits.
That's what I'm interested in.
Okay. So, okay, we have a model. We have a way of making a functional model. The problem is, everybody starts with functional models at the beginning, but they get obsolete, and they're useless. So what do? So what we're going to do is we're going to create an equivalence checker. Because I have found in my experience, if you have two representations of a circuit, one's stale, unless there is an active way forcing people to keep them synced. Okay, and that means we need to do equivalence checking. So how do we do equivalence checking? So remember, the model of an analog function is a matrix because it's a linear model. So y is equal to g times x, where g is a sort of a matrix of transfer functions. If I have that, I can extract out g from both the circuit implementation and from the model, and I can compare them and see if they're the same. Now, x doesn't need to be just linear. X could include powers if I was interested in third-order distortion or other things. There's lots of things I could do. This is fairly general. It just says there's a linear regression I'm running. Now, the thing is to figure out over what space I need to simulate. Remember, in digital, it's very hard because I have to simulate all the inputs. But for analog, it's smooth. So a random sampling of the input space will be very effective in just basically extracting what G is. So what we do is basically do that extraction. Now, we have to do a couple additional things because we have controllable circuits. And when you have a controllable circuit, that G is a function of the control variable. So what we need to be able to do is we need to be able to extract not only the transfer functions from the inputs to the outputs, but we also need to be able to extract the transfer function from the inputs to what we call pseudo outputs, which is basically the gain of, I'm sorry, I did the wrong thing. The pseudo output is basically the location of the pole or zero that's moving. So we have a characterization that we do for the different parts that allow us to characterize the circuit in a way that should match, that the functional model has to match. So if we have a variable, a variable gain peaking amplifier, then I want the functional model to have the variable gain of the peaking amplifier, and the control voltage better change the functional model the same way it does the circuit. Okay? Generating the inputs to extract what those parameters are not hard because the space is smooth. Now, the hard thing comes about because circuits today are not simply analog circuits. They have digital controls on them. Now, some of those digital controls change the circuit completely. If you look, this is a simple differential pair, but there are switches that change whether the inputs are actually the real inputs or the calibration inputs. If I calculate the transfer function when the switches connect to the real inputs, that is completely different than the transfer function when I connect the inputs to the calibration inputs, because that's a digital input. It changes the circuit. Similarly, if I check the circuit when it's in power down mode, that's a completely different transfer function than when it's not in power down mode. So what I end up doing is I need to basically completely enumerate all the digital inputs, because each of those are different circuits, and I calculate the transfer function for each of those different circuits. And my functional model better match all those circuits. Now, there are some digital inputs that are really analog inputs, like inputs to DACs, or just quantized analog inputs, and we treat those as analog inputs. So in general, the checking procedure is pretty simple. We label the ports of both the functional model and find correspondence between the functional model and the circuit, because those have to be given anyhow. For every true digital input, we generate a different circuit that we're going to validate. Then we go through and we generate random vectors within the constraints of the functional models. We do a linear regression, calculate what the statistics are. If they're too noisy, we do more. If we can't get the linear regression to work, we complain to the user that, look, the circuit isn't really as linear as you said. If the regressions work, we then compare the outputted circuit and model transfer functions. And whatever, power supply rejection, whatever you care about, right, is in that extraction and is modeled in that thing. So you can then say whether your models are good or not. One hopes that once we have a functional model done, what will really happen is you'll just run the circuit, it'll extract a set of parameters, those parameters will get put into the functional model. So this will happen automatically, and you'll continue running the system regressions with models that represent what's actually in the circuits.
The models are from the previous design
Let's say we're starting a new design.
No, when you start a new design, well, it depends. If the question is, are the models from the old design? It depends. If the blocks you're using are the same kind of block that you used before, then yes, you could use those functional model outlines, and you'd have to change the parameters to your parameters, but you wouldn't necessarily need to completely change the model. If you're building a different kind of phase lock loop than you built before, then you would have to probably change that model to model the effects that are important in this particular phase lock loop. But the hope is, look, we've been designing these things for a long time. Most of the blocks we use, we've designed before.
And then in the final, let's say the final verification, would you, like if you wanted to extract the layout, the reason I'm locking on to something that you said, substrate coupling.
Right.
Right? So substrate coupling is highly dependent on the layout and the particular implementation, that particular chip. So trying to extract that from the previous, I could see modeling maybe a transfer function.
So the point is, if substrate coupling was an important question, what you would do is substrate coupling is an important question. So there's basically a module in there which is substrate coupling. A substrate coupler model would take outputs from various points, because there are things that basically couple and other things that you don't, and generate inputs into the other sensitive nodes. So when you got to your model, you would have this model which is substrate coupling. So you'd have to extract it. You'd have to do a complete extraction of the substrate, do whatever you needed to do.
So the output of that extraction, the results of that extraction, would it go into feeding into this?
You have a functional model which is the substrate coupling. You have to do something that basically tells you what the parameters are from the various different nodes and what the additions are. Because typically you're not worried about very complicated linear transfer functions. It's through the substrate. It's just some attenuation. It's just some coupling coefficients. So that would probably be a matrix of coupling coefficients from outputs to inputs, small, that you would put in. That would be completely having to be done locally for your current chip. But the point of having this model is that you would have this model that says substrate coupling. So for a person who's never thought about it, they would say, what the hell is this module for? And some old beard, gray beard would tell them, oh, you have to do this thing. Run this three-dimensional simulator or whatever. Okay, so I want to end because we're supposed to end. So summary for model checking is that because the linear abstraction formally defines functions, a matrix of gain, we actually can formally say what the equivalence means, and we can use this to keep two things in equivalence. And my postdoc, former PhD student, has actually written a prototype tool that does this and works well. So the last thing I want to talk about is statistical analysis. I'm going to go through this pretty quickly because we're running a little late. Basically, I said that y equals gx, but g is actually not a single number. Every time you fabricate a chip, g is a different number. So you can think about g as actually being some other matrix to some random parameters that you're choosing. And the question is, can we take advantage of that? So at the system level, we can essentially do the Monte Carlo sims that you would like to do. And the answer quickly is yes, you can do that. And I'm going to skip that. The interesting thing is that there are two ways that parametric variations affect a circuit. The first way is to change the gain or bandwidth of the circuit. But the second way is actually to make the circuit not work. Because we can have situations where, because of some parameter value, the divider stops working, or some operational amplifier doesn't have enough compliance, or something that will cause the circuit to fail. That is, the linear model that we've made is no longer valid in that parameter space. And so what we do is we actually, in the functional models, we have an assertion that asserts what the parameter space is to make sure that the model still is valid. And the combination of changing the parameters and this assertion allows us to find most of the parametric variation errors that occur. Yeah?
The assertions, are they specific to a parameter, or do they end up being dependent on 50 other parameters? And now you've got essentially multiple matrices that result in a dependency of intervals in which it is valid and it is not valid.
Yeah, so the question is, do the assertions depend on a single parameter or multiple parameters? The answer are the assertions depend on multiple parameters. So what we do is, because we're choosing parameters from a distribution, depending upon how many parameters we're choosing in the distribution depends on how many parameters it can depend on. And we use some simple machine learning, hyperspace plane dividing things to find out planes that divide things, right? Because if you have a lot of parameters, you do a bunch of simulations, some work and some don't work. What we're trying to do is figure out what is the partition in that high dimensional space of those parameters that distinguish that. We do that. It's not clear that we get that perfectly, but as long as we partition the space roughly right, you'll get the idea of yield. It's not whether this particular parameter is going to work that you care about. What you care about is when I took parameters in a normal distribution for what I think the process is, do any of them fail, or what percentage of them fail?
So just a quick follow-up, and then so if you're relying on sort of this hyperplane partitioning, I imagine that's hard to quantify, but is the rationale that if I'm going to be on that boundary, I'm probably screwed anyway, so I'll just be close enough to know I'm in danger.
Exactly. So the idea is I want to partition the space to understand what percentage of the space I'm going to die. Now, if that space is small, it doesn't matter that the boundary is not exactly in the right space, because if 1% is going to fail, 1%. I'm not saying that if it says I work, I guarantee I'm going to work. I'm just saying if it says that 90% of the time I work, 90% of the time I'm going to work. Right. OK, so let me just summarize all this. So in conclusion, analog tools have lagged digital tools for a really good reason. One tool, like there isn't an electrical rule checker that works for all different classes of analog circuits. So it's not that analog designers are stupid or curmudgeons. They actually have a much harder problem to solve. But having said that, we are in a rut, and we need to do much better, and especially if we're going to continue to integrate these mixed signal blocks onto larger SoCs. So we can actually start leveraging some of the early things that were done in digital design to make analog design more robust. And basically, I think we can build a functional model of an analog circuit. I think we can do equivalence checking. I think we can basically archive the test to build up these electrical rules for different classes of circuits. And I think doing that will really make our life much easier. And the only way this is going to happen is if people believe and start doing that. So I'd like to ask all of you to try out these ideas, and if they work, try to push them forward. Thank you all for your attention.
All right, we have time for questions, I think.
Yes?
Do you have an example of a functional model, like on a backup slide or something, just to see what it looks like?
To look at what the Verilog code looks like?
Yeah. I mean, does it look substantially different than, I assume it must look quite different than ordinary Verilog.
I don't know that I have some. I'd have to scan through it. So if you're interested, come down. I can show some things to you. It looks different. It doesn't look that different from standard Verilog. What happens is it's an event-driven model. It consists of basically 3 pieces. So the first thing is the inputs come in. You calculate what the new output is. You compare the output to the current output to see whether you need to schedule or when you need to schedule, when the difference is big enough. And then you schedule the output. For digital systems, you typically don't do the scheduling explicitly because it happens intrinsically in the simulator. So there are some different calls. But the mechanics of it is not that hard. What's weird is you have to really understand what the essential features of that analog circuit are. And that's a skill that has to be developed. It's not easy to do. Yes?
So one of it's kind of a little bit different topic than what you're discussing. I just want to see if any implication to that problem. And the problem with analog, it doesn't scale as well as digital, so voltage, overhead, and margin, and accuracy. Is your methodology can help on that regard as well, or just lesser? It's nothing to do with.
Well, so the question is, look, the big problem with analog is that when you scale to a new technology, it doesn't scale that well because lots of things have to change. And is your methodology going to help with that? So I would say 2 things to that. The good news, the bad news for the world, the good news for analog designers is technologies are not scaling that much anymore. So frankly, this was a huge problem historically. I think it's going to be less of a problem moving forward. The second thing is the way analog designers have dealt with this problem is by doing more kinds of digital correction and building simpler analog circuits because you have less room to do things. And so what this methodology really is to make it easier to do the joint mixed signal digital simulations. I mean, analog digital simulations you need in a mixed signal chip. So I think it indirectly helps that. But it will still require people to cleverly come up with new topologies for the new technology. And that's good because if it didn't and it put analog designers out of business, they would never accept this tool. So the good news is that analog designers still have a good future. Yeah.
So take things a step
step further, do you see this tool being used to do like synthesis? Like you can use a circuit book as standard cells and go for synthesis of analog blocks?
Yeah, so the question is, could you use this tool to do synthesis? And I would say that looking forward, if you had all these things in place, could you leverage them in a synthesis tool? I think so. But if you think about synthesis, before you can ever build a synthesis tool, you have to have a really robust validation tool, because what synthesis really is trying things out and validating them. Okay? So if you think about the evolution of tools, the validation tools came first. And I also think that because analog is less discrete, more continuous, some of the synthesis problems are a little bit, they're sort of mixed integer, kind of problem. You vary parameters or you flip. And those optimization problems are a little more difficult than standard optimization problems. So I think it's doable. People have done it. But in order to do that, you need all the constraints and all the checks that I've talked about, because if you don't have that, optimizers always choose a really stupid answer if you don't constrain them. So I think this is a necessary first step. Yes?
I was wondering what you envision the sort of aggregation of knowledge and learning from these analog designers to be like. How do you envision this checklist being developed and becoming thorough? And is it like what parts are proprietary or not proprietary?
Yeah, well, okay. So the question is, how do I view these lists of checks being developed and what's proprietary and what's not proprietary? And I would say the bad news is that anything that's done within a company that does these checks will never leave, because that's kind of the lure of the designers in that thing, and they're disincentivized to actually share those. The good news is that if people in the university community decide to actually try to create these lists and share them, I think we could relatively rapidly get a set of basic checks that would be extremely informative. I mean, look, you can write checks in completely unintelligible ways. You can write them in ways that people could understand. So assuming that people write them in an understandable way, it would really be a way of disseminating sort of the key information about how you build things, because most of that is what you need to check. It's the coupling issue. It's the fact that you get spurs by the charge injection off the phase detector. These are things that are well known by anybody who builds that circuit, but unfortunately there are only like 5 people in the world who are actively doing it, and they tend to get bored and move on. So it's ephemeral knowledge, and so that's the advantage.
Do you think some of these tools actually already exist in terms of generating the level of abstraction? For example, one thing I could think of, could you build on some of the tools that exist? Harmonic balance might be one, for example. Everything we've talked about, we've kind of assumed time domain here, but I mean, that's one way of building you'd build your level, I guess, maybe not a level of extraction, but maybe well, actually, it is a level of abstraction.
So there are 2 places that you could say, look, any company that is currently building complicated mixed signal chips, so take any of the people doing Wi-Fi stuff, take any of the people doing wireline, all those companies basically have this kind of functional modeling going on internally. So people at Broadcom wrote a paper recently about the simulation environment they have. They have to do it because they're taping out this chip. It costs $50 to $100 million or whatever they're doing, and they need some way to validate it. And so they're doing this not as formally as I said, but they're basically doing these things. So I'm not claiming that anything I'm suggesting is actually new. I think people are doing it in bits and pieces already. I'm just saying, look, let's admit that this is what we're doing and basically try to get a set of tools that actually work together.
More uniform.
Yeah, well, so I can build these abstractions. We could publish them. There's support in Verilog to do that. In terms of doing other things than sort of time domain, the problem is that Verilog or digital simulation is intrinsically kind of time domain. So what we do, especially when we have to do domain translations, is I could basically extract out harmonic balance equations from my Verilog and from my circuit if that's the most important thing to think about. So I do spectral harmonic balance things. I just do time domain in Verilog. It's very fast. And then I do the Fourier transform to do the harmonic stuff. And I look at whether I'm getting the tones that I want. Right? There's no problem in doing that. But I think for digital simulation, modulo pulling out carrier effects, because I think we're going to have to do that. we're probably an event-driven times situation. Other questions?
All right, let's thank our speaker one last time.